I'm Zhenyu Dai, and I will talk about the Monte Carlo policy gradient estimator in math part, and I'm grouped with Jason Wang and Monte Zhao, and we'll talk about the card polo and the PyTorch code. So firstly, let me introduce this math part. So the outline is problem setup, stochastic optimization loop, policy gradient derivation, and Monte Carlo approximation. So firstly, we set up this problem. Based on the reinforced learning, if we only have a initial state S0, and based on this S0, it has an action, which is alpha t, in pi alpha t st, and it will give it to the environment transition, so the st plus 1, and get the reward rt. So, and the termination is episode ends at the terminal state st. So in this figure, it clearly shows how this happened. So we have S0, and based on this S0, it chooses alpha 0. So we get the feedback from the environment S1 and reward 0. And based on this S1, we have alpha 1. We choose action alpha 1. So we have S2, and we get the reward R1. And move on. Lastly, we have S tau and R tau minus 1 based on the environment. And this is how the reinforced learning happens. And what we need to do is to maximize this reward part. And let me introduce what the parameters we use. So firstly is the input is current state st, and the output is action distribution pi theta in the condition of st, and the parameter theta is the network weights and biases, and theta belongs to rd is what we optimized. So here we can just take in the theta to move it into pi theta, and the definition of expectation of the reward we can say is integral tau d tau r tau and p tau in the condition of pi theta, which means in the whole trajectory, the reward, the integral of the reward, and it's times the probability he chose this action in this theta. And we talk about the stochastic optimization loop. So if we input a parameter based on the system or environment, we can have a simulation output f theta, and we can add a gradient estimate, which we introduce here is del theta f theta. So based on these two parts, we can get the gradient based optimization. So use this new theta, which is back to loop to move on. So run current policy with theta. So collect trajectories, obtain estimator of f theta and del f theta. And key things is gradient estimate must be unbiased, or we will have a bias rewards from the whole loop. And we compare supervised learning and reinforced learning. So supervised learning, label data xy available, directly compute loss and gradient, f theta and del f theta are exact values, and dataset is fixed, which means in the fixed dataset, we have to change the theta. Just like the dataset is fixed. So we just to get the best algorithm, the best function to get the maximum rewards in the same dataset. But reinforced learning, no labels, only reward signals. And must run policy to collect data first. F theta and del f theta can only be estimated. Data distribution shifts with policy, which means based on the reward, we can change and to or how to say to optimize our f theta and del f theta to get the maximum rewards. So it is changeable. And the key thing is how to compute the gradient. So what we need to compute is this part, which we mentioned before in the reward part. And this is gradient of expectation, and it depends on theta. And we cannot naively differentiate the samples. And what we do next is to add a log in this part. And the right hand side can be estimated by sampling trajectories. So we'll mention after this page how this happened. So derivation in 3 steps. Firstly, write expectation as an integral. So we know this rewards is this integral, and we take gradient moving into the integral, which means here we get the del theta. So right hand side we add del theta to moving, so we have this part, and we apply the log derivative trick to replace this part, which means it just equals. We can see all the things are the same, and we have this del theta log p in tau in the condition of pi theta. And based on the chain rule identity, based on the chain rule, del log x equals del x over x. So we just move this x to here, get del x equals x times del log x, and we just let x equals this part. We have this part, and just move the things back to the last this part. So we have this, so it just like that. And how this log trick make it computable? So we can see this trajectory probability is a product of 3 parts. So it's mu as 0 and the mutable and pi theta alpha t in the condition of st, and this and the pi p st plus 1 in the condition of st and alpha t, which means this part is our initiate state, and this part is the probability with how to say action distribution multiple, and this is multiples and multiple all the environment feedback from this part. And we cannot get this part because it is always be like a no for us, but we need to have something to remove it, so we just let it become a log. So here multiple will become a sum, and so we just become all the log, and we differentiate theta. So this part doesn't include theta, this part doesn't include theta, so they can be seen as 0. So only this part left. And after remove this environment, this is the theta, which is our parameter, so we can get this part result. So this is how the algorithm happens. And lastly, we have Monte Carlo approximation. So we can say in this part is the same as this part. So which means we can sample n trajectories, take advantage. So it can be seen as sample-based estimate, which we will use in the PyTorch. And this part requires integrating over all possible x intractable in practice. So this is how it happens, and thank you. Let's move it to Jason.
Okay, hi everyone, I'm Jason. I'm introducing couple, the environment we use to train the reinforcement algorithm. The couple is a simple physics simulation. As you can see on the right, there's a cars on the truck with a pole attached to it. Our goal is simple, just keep the pole upright as long as possible. The longer you survive, the higher you score. And each step, we can only do one thing, push the car left or right. And every step survive earned 1 point with a maximum of 500 points. And at the start of each episode, the four values, the car position, velocity, angle, and angular velocity, they are all randomly symbols between negative 0.05 to positive 0.05. So every episode starts different. The episode ends if any of the following occurred. The pole tells more than plus or minus 12 degrees. The card goes beyond plus or minus 2.4, or the episode exceeds 500 steps. So how does the AI agent know what is happening in the environment? It relies on the state we call S. And in each step, the environments give an agent 4 number, like 1, 2, 3, 4, we just talked about before. So the first one, the car positions, which means that where the car currently is, and there's a range. Like there's an example 0.02, which means that the car is slightly to the right. And the second one is velocities, which means that how fast the car is moving. And there's the range. And the example is negative 0.01, which means that the car is slowly driving left. And the third one is angle, which means that how much the pole is tilting, and it's a range. And there's an example 0.03, which means that the pole is slightly tilting right. And the last one, the angular velocities, which means that how fast the pole is falling. It is the range, and it's example 0.01, and which means that the pole is still is nearly still. And there's an example at the bottom. So when an agent sees this state, you need to decide whether to push left or right. How the agent make these decisions is the problem that the reinforcement algorithm solves, which we will discuss later. Okay, so now we understand the couple environments. Let's move on the reinforcement algorithm. The first part is the object. So the goal of reinforcement is to find the best theta to maximize the average total rewards. So what is theta? It is all the weight in the neural network. Adjusting theta means adjusting how the agent make decisions. So this formula here is saying given the current theta, what is the average total reward we get from playing the game? And let's see the breakdown. So J of theta is the average total rewards. We want to maximize this. And theta, it is all the weights in the neural network. And it's gamma. It is a discount factor. Like for example, 0.95. It makes earlier rewards more valuable than later ones because earlier actions have a bigger impact on the whole episode. And the next one is R sub T is the reward at each step. Like in carpals, every step survives gives plus 1 point. And the E is an expected value. It means averaging every many episodes. Like, okay, so in the example here, with the gamma equal to 0.98 and fast step survive, the discount rewards are like this, these calculations. And we got a J of theta equal to like 4.803. This is total rewards for these episodes. Our goal is to make this average higher and higher. Okay, so how do we make J of theta higher and higher? We use the gradient. So the gradient tells us which direction should we adjust theta so that the zeta theta increase. So with the gradient, we can note the policy step by step toward better performance. And before computing the gradient, we first need to compute a return to go for each step. So the formula is like this. So in Planck's term, is like how much discount total reward can we still get from this step onwards. The larger g sub t is, the better the performance after this step. Okay, so the gradient estimate g hat here equal to over n. It times the sum over all episode and all times that of nabla theta log pi here. So let's break down. So n is a number of episodes, and nabla theta log pi tell us which direction to adjust theta to increase the probability of this action. And importantly, Python compute this automatically, so we don't need to calculate it by hand. And the third one, g sub t determines how big the update is. The better performance means a bigger update. 1 over n average over all episodes. And looking at the example on the right here. So like episode 1 went right. Here. Okay. This is 3 steps and computing GT backward and so on. And then we got their gradient estimate score. Okay, now so let's put everything together. So this is a complete reinforcement algorithm in 4 steps. So the first step is initialize theta. So we randomly set all the weights in the neural network. Like for example, weight 1, weight 2 is blah blah blah. Yeah, and it has no idea what it's doing in the beginning. And step 2, we equalize an episodes and compute g sub t for each step. For example, like it's running 3 times 1, 2, 3, and you get every like g score. And then the third step 3, we form the gradient estimate g hat. So we sum up all the contributions from every step of every episode, then divide by n, given g hat equally is 0.33. And then step 4, update theta. So the theta is the formula is theta equal theta plus alpha times g hat here. So alpha is the learning rate. We control how big each update step is. Like for example, we say it's 0.0002. So theta plus like the formula here. So every weight get not like slightly, and the policy become a little bit better. Okay, so then we go back to after the first step, we go back to the step 2 and then repeat. After update 1, the average is 2 steps. After update 100, it is 150 steps, and so on. The policy goes from completely random to actually knowing how to balance the pool. Okay, so right now Melody will explain Python code.
Okay, hi, this is Melody. So I will work through the PyTorch code from reinforce. My teammates cover the math, so I will just connect each formula to the code line by line. So I will do it in 3 parts: the policy network, how we connect episode and the training step. So one thing I want to remind in the code field, the band trainer step comes before the collection episode. Because the class is defined first, but I will follow the execution order, policy, then collecting data, then update. Okay. First, let's come to the policy class. So this is the policy pi of action a given state S. Theta is just the weight and the bias of these two layers. FC1 maps the state OBSDIM to 128. FC2 maps to ActDIM. For card pull, that's 4 inputs, 2 outputs, left or right. In forward, we pass the state through the FC1, yes, with ReLU, and then FC2 with softmax. The output is probability over actions. That's the policy pi of a given S. Okay, let's go to part 2, collection episode. In the main, we create the card pull ENV and set the hyperparameters. The bench size is n. We collect n episode per update. Gamma is discount factor. And we can also say there are 2 for loops. Outer loop is training steps. Inner loop collects n episode. Each episode is 1 pass from reset to down. So, and then let's see the while true. There are 4 steps. Step 1 is get props. It converts the state to tensor. So feed the policy, feed it to policy. We get props. That's the policy at state S at time t. Step 2 is sample actions. Categorical turns props into distribution. We sample from it. So action at time t is sampled from the policy. Step 3, ENV step give us next state, reward, and dawn. Step 4, we store log props, reward at t. So we store a log prop, not prop. So the gradient formula use the gradient of log pi. So we need log. We also store reward at time t for computing return g at time t later. So why log? Because the gradient is the gradient of log pi. If we stored prop, we'd have to take log later anyway. So let's go back to part 3. Yeah. The band trainer steps. In step, we can see from here. Yeah. In step, we first 0 grand to clear the old gradients. Yes, here. And for each episode, we need G at time t. The discounted sum of future reverse from time t. We compute it backwards. Reverse EP goes from the last step. R start at 0. Each time R equals rewards at T plus gamma times R. In other words, GT equals RT plus gamma times G sub T plus 1. That G sub T plus 1 is the R on the right. So we compute it in the last iteration. Since we're iterating backwards, then we reverse the list, so return a line with time order. So we go backwards because G at T depends on G at T plus 1. Let's see this part. So we normalize the returns. Subtract mean, divide by standard. This is variance reduction. It doesn't change the direction of the gradient, just makes the scale more stable. Adam works better this way. And the loss is 1 over n times the sum of minus log pi times g at time t. The minus sign PyTorch does gradient descent, but we want gradient ascent, so we minimize the negative, same effect. So we want to minimize log pi times g at t, minimizing the minus log pi times g at t does it. So here is backward and step. Loss backward computes the gradient. Optimizer.step does theta equals theta minus alpha times gradient of L. So since gradient of L equals minus the policy gradient estimator, that's theta equals theta plus theta times the policy gradient estimator. One gradient, ascent step. So let's see the last part. So we report AVG return per episode. In Carlo, reward is 1 each step. So return equals how many steps we survived. Higher is better. So we can see what I run. The average return per episode keep increasing during training. You can see it's keep increasing. So the loop is collect an episode, compute G at time t, compute loss, backward, step, repeat. That's reinforce. To recap, we connect the policy network to pi, the connection loop to sampling from pi, and the trainer to the gradient formula. Everything in the code maps directly to the math. Okay, thank you for listening.